Hello everyone, this is Sarvesh. In this video we'll be solving question 3 of 6 required for MAT104 Endsem. Okay, so in this question we have been given an ODE which is depicting a mass spring system. It's given by the ODE y double dash plus 25y equals 24 sin t, and we are given two initial conditions. So we have to graph the solution curve, and in addition graph the curve of y equals yp, and then we have to see when the system practically reaches a steady state. Okay, so our model is depicted by our ODE y double dash plus 25y equals 24 sin t. Okay, let's first try to see how much we can actually how much information we can actually gather from this model with this equation without actually solving it. So we can see that this thing only has one coordinate axis which predicts which tells us the position of the mass. Basically y is a function of time, and y is the only thing which tells us where the position is. So maybe it may be something like this. It's just an example. The mass spring system is like this. So y might be the distance from the base, and only y is giving us information about the position of the mass. So we need only one independent coordinate axis to tell us where the mass is. So this would mean our model is of 1 degree of freedom. So basically if you have n degrees of freedom, you would need n independent coordinate axis to give us the position of the masses. So in those cases you might have multiple masses and multiple springs, but here we have only 1 degree of freedom. So what else? Now we can see, now we also know that the damping is proportional to the velocity of the mass. So how the faster it moves, the more the viscous damping it would face. So again, I'm depicting only the viscous damping. Other dampings would have other characteristic, but here viscous damping is proportional only to the velocity of the mass. So velocity is again y dash, which means our damping constant depends only on the velocity. So here we can see that in a model there is no y dash. If you want to write it explicitly, we can write it as plus 0 times y dash, which would mean c is our damping constant, and here since c is equal to 0, our damping constant is equal to 0, which means basically our system is undamped, which means if by chance our system is brought into motion, it would continuously oscillate. It would never end. There would be no force which would bring it back to rest. Okay, so our system is undamped. So we know that now. So let's actually go to solve our equation. Our equation is y double dash plus 25 times y equals 24 sin t. Now we can see this is a non-homogeneous equation. So a non-homogeneous equation would have two parts. It would have the yh and yp, the homogeneous part and the particular part. Our homogeneous part can be solved by assuming y double dash plus 25y to be equal to 0. Basically we'll be assuming this right hand part to be equal to 0, and we'd solve this. We'll get a characteristic equation, and based on that we'll have our y, and then we'll find our homogeneous part. Our y particular part will be found out by assuming a y to have would be basically some function, or it would assume to be of some form, and that form will be based upon our right hand side, and we'd find our y dash and our y double dash, substitute it back into our equation, and hopefully we'll end up with our y particular. So let's first solve the homogeneous part. So the y homogeneous part would be equal to, let's solve that. So y double dash plus 25y is equal to 0. So we'll be assuming our y to be taking the form e to the power rx. Sorry, it would be of the form e to the power rt. Now since y is a function of time, it would make sense for us to put time here instead of x. And our y dash would be r e to the power rt, and y double dash would be r square e to the power rt. And we just substitute this back into our equation, and then we'll get our characteristic equation. Or instead you can just substitute, instead of y double dash you can substitute r square, and instead of y dash you can substitute r and y equals 1. Instead of y, you can substitute 1. So this is basically simplification of all of this. If you substitute these values, you will get e to the power rt common, and it would get cancelled with the 0. But here you can just like that substitute. I mean, if you substitute this or this, it's basically the same thing. That's what I'm trying to say. So our characteristic equation would be r square plus 25 is equal to 0. So r square would be negative 25. So our roots would be plus or minus 5 times I. So our root is of the form lambda plus or minus mu I. Well, plus or minus 5i can be written as 0 plus or minus 5i. So lambda would be equal to 0 and mu would be equal to 5. Since our roots is of the form this way, and so our general solution, our homogeneous part, would assume the form e to the power lambda x c1 cos mu t. Sorry, this one would be t. Y is a function of time always. So c1 cos of mu t plus c2 sine of mu t. Okay. So we know lambda is equal to 0 and mu is equal to 5. So let's substitute here. So yh will be equal to c1 cos phi t plus c2 sine phi t. So we have found our homogeneous part. Now let's try to find our y particular part. So our yp is nothing but 24 sine t. So we know the right hand side of the equation is 24 sine t. So let's assume our y particular to be of the form a sine t plus b cos t. So our y p dash, actually rather let's keep it as y. Okay, so our y dash would be a cos t minus b sin t. Our y double dash would be minus a sin t minus b cos t. So now we have these three values. Let's substitute it back into our original equation. Our original equation is y double dash plus 25 times y equals 24 sin t. Let's substitute it. So y double dash would be this minus a sin t minus b cos t plus 25 times y, nothing but a sin t plus b cos t is equal to 24 sin t. Okay, so this would mean minus a sin of t minus b cos of t plus 25a sin of t plus 25b cos of t equals 24 sin of t. Okay, so this would mean sin of t, I'm taking sin of t common from these terms, so that would give us negative a plus 25a plus cos of t times minus b plus 25b equals 24 sin t. So let's compare the coefficients in either sides. So comparing the coefficients of sin t, that would mean 24a is equal to 24, which would mean a is equal to 1. And comparing our coefficients of cos t, well, explicitly you can write 0 times cos t, that would mean minus b, sorry, this would mean 24b to be equal to 0, which would imply b to be equal to 0. Now we know a is equal to 1 and b is equal to 0. Let's substitute it back into our assumed form over here. So our yp will be 1 into sin t plus 0 into cos t. Basically our yp is nothing but just sin t. So general solution, y is nothing but a y homogeneous plus y particular, which is nothing but, we found our y homogeneous. Our y homogeneous is c1 cos phi t, c1 cos phi t plus c2 sin phi t plus our y particular, and y particular is nothing but sin of t. So this is our equation of motion, a solved equation of motion. Sorry, a solved solution. Equation of motion. It's basically the equation of motion. So we still have to find C1 and C2. So we can find those out with the help of our initial conditions. Now I'll explain what this graph is later, but let's first solve this. So we know y of 0 is equal to 1. Let's substitute this in our equation. So left hand side would become 1. C1 into cos of 5 times 0 is cos of 0, which is nothing but 1. So this value would become 1, plus C2 times cos of 5 times 0 is sine of 0. Basically this would become 0 then. So then sine of 0 is 0. So here we found out C1 is equal to 1. So now our solution would be y is equal to cos of phi t plus C2 sine of phi t plus sine of t. Let's find y dash. Y dash is nothing but negative sine of phi t times phi plus C2 cos of phi t times phi plus 1. Sorry, plus cos of t. Okay. So now we know y. We are there. It was also given that y dash of 0 is equal to 1. So let's substitute that in our equation. So left hand side will become 1, which is equal to sine of 5 times 0 is 0. So this entire one will become 0. So this would be 0 plus C2 times cos of 5 times 0 is 0 is 1. So C times 1 times 5 plus cos of 0 is 1. So this would mean, or 1 and 1 would get cancelled. So C2, 5 times C2 is equal to 0. Basically means C2 is equal to 0. So now our final equation would reduce to cos of phi t plus C2 times phi t plus, but C2 is equal to 0. So this entire one would become 0. So it would be just cos of phi t plus sine of t. So this would be our solution of the modeled equation. Okay, this would be, so let's try, they've asked us to sketch the graph of solution curve. Now let's sketch the graph of the solution curve. Okay, how do you sketch this? Now for now, do not assume the first term, but just consider the second one. Now time is extending both ways. Time is extending from negative infinity to infinity. Okay, so basically, which would mean just the sine graph. Okay, so I can just draw the sine graph on either side. Okay, I can solve the sine graph. Now let me add this term. So basically what this term does is it adds the cos of phi t terms along at each point of sine of t. So at each and individual point of the sine graph, I would be adding cos of phi t. Okay, so now if I were to add plus cos of phi t to this graph, which is nothing but sine of t, so I'll be having, so it would not start from 0 here, but since cos of 0 is 1 and sine of 0 is 0, so I can start from here. But what would happen is it would still assume some form like this. But what will happen is cos varies at each and every point. So basically, I'll be getting a curve like this. So this would be, the inner one would be ours, would be more or less a sine graph, but a sine graph would be something like this. But again, I'm just saying, it would follow a similar pattern like our sine. It's basically cosine here, but it would basically, it's more or less following the same graph. Okay, so our graph, our final graph should look something like this. It will extend on either sides, same way. Okay, so that's what I've modeled it on MATLAB, and this would be our solution. This would be the graph of the solution. Okay, the red one you see here, the red line you see in the interior one will be our y particular, which is nothing but just the sine of t. The blue one is The blue one you see over here is our actual solution, which is cos of phi t plus sine of t. Here as you can see, here you can see that, let me erase this. Okay, here you can see that the y particular starting from 0, but the actual solution starts from 1, because we just said that cos of 0 is 1 and sine of 0 is 0. So it makes sense if it starts from 1. What else can you figure it out? Here you can see that the frequency of cos is 5 times greater than the sine. So when sine goes all the way from 1, it completes one wavelength, it should complete, it's basically 5 times the same frequency. So as you can see, from one value of 0 to the peak to the other 0, the same cos should have oscillated 5 times. That's what you can see. Like, let's consider here from the 0 to values, it should have oscillated 5 times. Cos should have made this entire graph oscillate 5 times. 1, 2, 3, 4, 5. This would happen for the other things as well. So if you consider from this one to this one, you can see that 1, 2, 3, 4, 5. Basically, cos of phi t makes it oscillate 5 times along one peak or one crest. Along one peak or one crest, this is what makes it oscillate 5 times. And sine of t basically helps take this entire graph in a cosinally or a sinusoidal way, more or less. Okay, so what else have they asked? Okay, they've also asked us to sketch the graph of y equals y of p. So y is equal to y of p. It's very easy. So y of p, as we know, is just sine of t. So this would be basically just the sine curve. Basically the sine curve. This would be 0. This would be pi by 2. This would be pi. This would be 3 pi by 2. So more, it would extend similar way in the either way. It's just the sine curve. Okay. Now they've also asked us to find the when does the system reach a steady state? See, the steady state and the transient state occurs only when there is a damping. So like I said, once this we have already found out our system is undamped, so there is no steady state. At t is equal to infinity, this one would still continue. Basically this same pattern would keep on continuing. The same pattern would continue no matter what. It would just continue. It wouldn't come to rest at all. Okay, so that there is no steady state. Like, there is no transient state or steady state. There is no transient state or steady state. It's just a complete, it's an infinite oscillation of the spring mass system. Okay, since there is no damping, it doesn't make sense to actually define a steady state and a transient state. There is no separate definition between both. Okay, so this is the solution of our given equation. Okay, as you can see, what do I mean by no steady state is that I have modeled the same graph all over again, but over like a very long, is like for 100 pi I think. So the time extending from 0 to 100 pi. So here, as you can see, it's just continuation of the same thing all over again and again, so that it wouldn't come, since there is no damping, it wouldn't die down or increase. It's just gonna keep on continuing. So there is no definition of steady state here. See, as you can see, even at time is equal to infinity, what is going to happen is, even as t approaches to infinity, all we can say is that cos lies from -1 to 1 and sine lies from -1 to 1. All we can really say is, from this graph, at t is equal to infinity, its interval would lie from this maximum value to its lower value. Apart from that, there isn't really much that can be said, rather.